Imagine boarding a ship and knowing you will die long before it lands. So will your children and grandchildren. Only their distant descendants will arrive. This isn't a spacecraft. It's a sealed world carrying thousands of people, built to run 400 years without a single delivery. No resupply, no rescue, no way to turn back, ever. Every breath recycled, every drop of water used 10,000 times. One system fails with no backup, and everyone aboard dies. So why build something this lonely? Because 4.24 light-years away sits Proxima Centauri, the closest star to our Sun, and around it, an Earth-mass world where liquid water could survive. But there's something worse than failure. Arriving to find a faster ship already there, launched long after them, sitting on the ground they died for. This is the longest voyage humanity may ever attempt. Tonight, I'll show you all of it, how it moves, how it survives, how it arrives, and what 400 years does to the people inside it. Now get yourself comfortable, hit subscribe. We begin. Somewhere in the future, maybe a century from now, maybe longer, humanity makes a choice it can never take back. Not a choice to visit another world, a choice to leave for one. To tear a small piece of itself away from Earth and hurl it at another star, knowing, before the engines even light, that most of the people who leave will die somewhere in the dark, long before they ever arrive. And here is the strangest part. They would go anyway. To understand why anyone would agree to such a thing, why a civilization would spend more wealth than it has ever spent on anything to send its own children into a place that will almost certainly kill them, we have to begin with a single, simple question. If we were ever going to leave, where would we even go? The answer is chosen for one reason above all others. Not because it's the most beautiful, not because it's the most likely to hold life, simply because it's the closest. Its name is Alpha Centauri. And when you look up at it, from the southern half of the world, low on the horizon, it looks like a single bright point, the third brightest star in the entire night sky. But that's an illusion of distance. Alpha Centauri is not one star at all. 3 stars, bound together by gravity, circle one another in a slow gravitational dance older than the human species. 2 of them, called A and B, are much like our own Sun. The third is a small, dim red ember of a star named Proxima Centauri, and Proxima holds a quiet record. Of every star in the sky, it's the nearest to our Sun, our closest neighbour in the whole galaxy. So how close is close? Just over 4 light-years. And a light-year is one of those numbers that slides straight through the mind without leaving a mark. So let's slow down and feel it. Light is the fastest thing that exists. It crosses from the moon to your eye in about 1.5 seconds. It reaches us from the Sun, 93 million miles away, about 150 million kilometres, in roughly 8 minutes. A light year is how far that beam travels in a full year, never slowing, never stopping. Proxima is more than 4 of those away. There's a way to hold this in your hand. Shrink the Sun down to the size of a grapefruit and set it on a table in front of you. On that same scale, the Earth becomes a single grain of sand, circling about 10 meters, 30 feet, away. And Alpha Centauri, the very nearest star, would be another grapefruit, sitting roughly 2,500 miles away, about 4,000 kilometers. The width of a continent, 2 pieces of fruit on opposite coasts of a country, with nothing but empty table in between. That empty table is what a starship has to cross. But astronomers didn't choose this star only because it's near. They chose it because something might be waiting there. In 2016, using telescopes high in the mountains of Chile, astronomers at the European Southern Observatory found a planet circling Proxima. They named it Proxima b, and it isn't some bloated ball of gas. It's a rocky world, at least a little heavier than Earth, sitting in what scientists call the habitable zone. That phrase deserves a moment, because everything hangs on it. The habitable zone is simply the narrow band around a star where it's neither too hot nor too cold. where water, if any exists, could stay liquid instead of boiling away or freezing solid. Too close to the fire and your oceans evaporate. Too far and they turn to ice. Proxima b sits in the thin ring in between, the Goldilocks band, a roughly Earth-sized world, possibly with liquid water, orbiting the nearest star to our own. If you set out to design a reason to leave home, you could hardly do better. And then, more recently, the story deepened. In 2024, the James Webb Space Telescope, the most powerful eye humanity has ever built, turned toward the brightest of the three stars, Alpha Centauri A, and glimpsed something faint sitting beside it. A possible giant planet, roughly the mass of Saturn, hiding in the glare. Finding it at all was almost miraculous. Picture trying to spot a single firefly hovering right beside the beam of a lighthouse from miles away. This planet was more than 10,000 times fainter than the star it clung to. For a moment, it seemed we'd found a whole new world in our nearest neighbouring system. But then, it vanished. When astronomers looked again in 2025, the planet was gone. 2 more careful searches and still nothing. To this day, its existence remains unconfirmed. A flicker that may have been a giant world caught mid-orbit, slipping too close to its star to be seen, or may have been nothing at all. Scientists are still arguing over it, and honestly, they may not settle the question for years. So this is what waits for us at Alpha Centauri. A rocky world in the Goldilocks zone that might, just might, hold life. A ghost of a giant planet that keeps disappearing. A system close enough to dream about, and just barely close enough perhaps to reach. That is the prize. Now here is the wall. 4 light years sounds almost gentle, only 4. But that one word, light, is doing a monstrous amount of hiding. Written out in plain distance, just over 4 light years is roughly 40 trillion kilometres, about 25 trillion miles. And a number that large stays meaningless until you try to actually cross it. So let's try to cross it with the fastest machine our species has ever built. Right now, the fastest object humanity has ever launched into deep space is a spacecraft called Voyager 1. Launched in 1977, it's still racing away from the Sun at about 17 kilometers every second, around 10 miles per second. At that speed, it would cross the entire United States, coast to coast, in about 5 minutes. That is genuinely, staggeringly fast. Faster than any human being has ever travelled. And it's nowhere near enough. If Voyager were aimed straight at Proxima, it isn't, but if it were, it would need more than 70,000 years to arrive. 70,000 years. Let that number settle. Look back that far into our own past, and you reach the age when our ancestors, small, scattered bands of modern humans, were only just beginning to walk out of Africa and spread, for the very first time, across a wild and empty planet. Everything you would call history, every city, every empire, every word ever written down, fits into the last 5,000 or 6,000 years. Our single fastest machine would need more than 10 times the whole of recorded history, just to cross to the nearest star. Our fastest machine. 70,000 years. And still, that's the fast option. Here, then, is the problem the entire journey is built around. No human being lives 70,000 years. No human being lives even 200. If we are ever going to cross that gulf, the voyage has to be longer than any single life that begins it. The mission has to outlive its crew, which leaves engineers staring at a strange, almost unthinkable question. How do you carry a human being across a distance no human can survive? They have found only 3 possible answers. The first is the one you've probably seen in films. Freeze the crew. Not kill them, slow them. The idea is called torpor, and it isn't pure fantasy. NASA has funded serious studies of it, led by an aerospace company called SpaceWorks, and the model comes straight out of nature. Watch a bear in deep winter. Its heart slows to a crawl. Its body cools. It stops eating entirely, burning only a slow trickle of its own fat for months on end, and in spring it wakes, thin but alive. A sleeping crew would do something similar. By lowering body temperature and dropping the metabolism, the rate at which the body burns fuel, some estimates suggest by half or more, perhaps as much as 70%, a hibernating traveller would need far less food, water and air. Bodies at rest, drifting through the dark, waiting to be woken at the end. But the dark does not leave sleeping bodies alone. Space is soaked in radiation, high-speed particles that pass straight through metal and flesh alike. Across a few months to Mars, the risk is manageable, but stretch that sleep over centuries, and those particles keep coming, silently, ceaselessly, quietly damaging cells that are no longer repairing themselves the way a fully awake body would. We simply do not know whether a frozen human could survive a sleep that long intact. No one has ever tried it for more than a few days. So the sleeper ship remains a beautiful, uncertain gamble. The second answer is stranger and colder and in some ways more clever. Don't send adults at all. Send the beginnings of them. This concept is called embryo space colonization. Instead of grown people, the ship carries thousands of frozen human embryos. Human life at its very earliest stage, so small that thousands could fit inside a container you could hold in 2 hands. No meals to pack, no air to recycle, no gravity to fake, no generations to keep alive across the centuries. Just a tiny frozen cargo and a fleet of machines. The machines would do everything else. On arrival, artificial wombs would thaw and grow the embryos into children, and robots, patient, intelligent, tireless, would raise them, teach them to speak, teach them who they are and where they came from, and why a world they have never seen sent them across the stars. Strip away the food, the water, and the living crew, and the ship becomes almost unimaginably lighter. And in this business, lighter means possible. But think for a moment about what that childhood would be. The first human beings at another star, born light years from any other person, with no mother, no father, no grandparent, raised entirely by machines, carrying out instructions written by people who died before the children were ever conceived. Whether a human raised that way would grow up whole, we cannot say. We have never done it. We may not truly know until someone tries. And that brings us to the third answer, the boldest of them all. Don't freeze anyone. Don't send embryos. Send people, awake, alive, ordinary people, and simply accept that they will never see the destination. This is the generation ship, a vessel so vast it stops being a vehicle and becomes a small, moving world. Aboard it, people live full lives. They fall in love. They raise children. They grow old. And they die. All inside the ship, in flight, somewhere in the endless dark between the stars. Their children are born aboard and grow up and have children of their own and hand the mission forward. And on it goes, life after life, for however many centuries the crossing demands. The people who arrive would be the distant descendants of the people who left, great-great-grandchildren, carrying out a promise made by ancestors they never met. It's the heaviest option, the most expensive, the most fragile, and, unmistakably, the most human, because it asks people to spend their entire lives on a journey whose ending they will never witness, to plant a seed in soil they will never walk, for a shade that will fall on someone they will never meet. That single, quiet act, giving your whole life to a place you will never reach, sits at the heart of everything that follows. And yet, before a single bolt is tightened, one cold piece of arithmetic argues that the whole thing might be a mistake. Here is the trap. Technology keeps getting faster. The ship we could build 2 centuries from now would be quicker than the one we could build today. So imagine you launch your generation ship now, at the best speed you can manage, and it crawls off into the dark for 400 years. Then, a century after you leave, someone back home builds a faster ship. It launches, overtakes you in mid-voyage, and reaches Alpha Centauri decades before you do. Your descendants would arrive to find the world already settled. Their entire voyage, every life lived and lost aboard, rendered pointless before they even land. An engineer named Andrew Kennedy studied this exact problem and gave it a name, the weight calculation, and his conclusion is genuinely unsettling. If you expect technology to keep improving, then leaving too early can waste the whole mission. Sometimes the smartest move is simply to wait and let progress do the traveling for you. But, and this is the twist that saves the dream, waiting carries its own danger. Wait too long, and the moment can slip away entirely. Fortunes fade. Civilizations lose their nerve, or their wealth, or their will. The window standing open today may not be open in 300 years. Kennedy's own mathematics admits it. At some point, waiting stops helping and starts costing you everything. So the decision cannot be postponed forever. Eventually someone has to choose, go now, or risk never going at all. And in this future, we're imagining, after all the arguing, all the mathematics, all the warnings, the choice is finally made. Build the Ark, not the sleeper ship, not the embryo ship, the hardest one, the living one. A world with a crew that will be born and grow old and die beneath an artificial sky, carrying a promise across 4 centuries of darkness toward a pale red star. The decision, it turns out, is the easy part, because the moment that choice is made, humanity runs headlong into a problem so enormous, it makes everything before it looks simple. A generation ship isn't a rocket, it's a world, millions of tons of rock and metal and breathing living things, and somehow that entire world has to be pushed to a speed no human machine has ever come close to reaching, and then, at the far end, brought to a stop. Before anyone can live aboard the Ark, someone has to answer the first impossible question. How do you move a world? Not a rocket, not a capsule. A world, millions of tons of rock and metal and water and breathing things, pushed to a speed no machine has ever reached, and then, at the far end of the dark, somehow brought to a stop. To even begin, we have to defeat a single equation. A piece of mathematics so unforgiving that engineers speak of it the way old sailors once spoke of the sea, with respect and a little fear. A nearly deaf Russian schoolteacher named Konstantin Tsiolkovsky wrote it down more than a century ago, working alone, far from any laboratory, and it describes the cruelest trap in all of rocketry. To go faster, you need more fuel, but fuel has weight, and that weight needs even more fuel to move it, which adds more weight, which needs more fuel again. Picture crossing a burning desert on foot, carrying all your water on your back. The farther you mean to go, the more water you must carry. But water is heavy, so the more you carry, the more you need just to haul the water itself. Push that logic far enough, and the load turns impossible before you've taken a single step. That is the rocket equation. And ordinary chemical rockets, the kind lifting every astronaut alive today, lose that fight before it even starts. They release far too little energy for every kilogram they burn. Racing them to another star would be like trying to bail out the ocean with a teaspoon. So the dreamers went looking for a bigger fire. The first serious answer was almost insane in its boldness. If you want the most violent energy humanity has ever unleashed, then use the most violent energy humanity has ever unleashed. Use nuclear bombs. In 1958, a team at a company called General Atomics, including the brilliant physicist Freeman Dyson, began designing exactly that. They called it Project Orion. The idea was to build a colossal ship with a thick metal shield at its base, a pusher plate, and then to drop small nuclear charges out the back and detonate them, one after another, behind the ship. Think about what that means for a moment. You would ride to the stars by setting off an atomic bomb beneath you, catching the blast on a giant plate and surfing the shockwave, then doing it again and again, thousands of times, each explosion kicking you faster into the dark. And here is the staggering part. On paper, it worked. Dyson calculated that a version of Orion, riding its own chain of detonations, could reach a few % of the speed of light, enough, in the more optimistic designs, to cross to Alpha Centauri in roughly a century or so. Not 70,000 years. A single long human lifetime, stretched across a few generations. For a brief moment in the early 1960s, a starship felt almost within reach. But there was a problem, and it wasn't physics. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty, forbidding the detonation of nuclear devices in the atmosphere and in space. Overnight, the very thing Orion needed to do, set off bombs above the Earth, became illegal under international law. 2 years later, the funding vanished entirely. The only starship we've ever designed that could be built with something close to existing technology was killed not by an equation, but by a signature on a page. So the dream moved on, from bombs to something cleaner. The next great answer was fusion, the same process that powers the sun, forcing the nuclei of light atoms to slam together and release enormous energy, but harnessed inside an engine. In the 1970s, the British Interplanetary Society gathered a dozen scientists and engineers to design a real fusion starship. They called it Project Daedalus, and their probe was meant to reach around 12% of the speed of light. That number deserves to be felt. 12% of light speed is fast enough to cross from the Earth to the Moon in roughly 10 seconds, a journey that took the Apollo astronauts 3 days. At that blistering pace, Daedalus could reach a nearby star in a matter of decades rather than eons. But there was a catch, and it's the catch that haunts this entire story. Daedalus was never designed to stop. It was a flyby probe, built to scream past its target at 1/10 of light speed, snapping what data it could in the few hours it had, and then hurtling on into the emptiness beyond, forever. It could reach another star. It could never stay. Which raises the question almost everyone forgets to ask. What good is arriving if you can't stop? One project took that question seriously. In the late 1980s, the US Naval Academy, together with NASA, designed a probe called Longshot. And Longshot was built around a single, quietly radical goal. Not to fly past Alpha Centauri, but to arrive there and enter orbit. Riding a pulsed fusion drive, it would take about a century to reach the system, cruising at roughly 4.5% of light speed. Slower than Daedalus, yes, but it would carry enough power to break at the far end and slip into orbit around one of the stars, to become a permanent visitor instead of a passing ghost. Longshot proved something profound, at least on paper. A starship doesn't have to merely pass its destination, it can stop. And stopping, as we are about to see, is where the real nightmare begins. But first, the fuel. If you asked a physicist for the ultimate rocket fuel, the most powerful substance the laws of nature allow, they would give you a single word: antimatter. For every ordinary particle in the universe, there exists a mirror twin with the opposite charge. It's antiparticle. And when matter meets antimatter, something extraordinary happens. They don't just burn, they annihilate. Both particles vanish completely, their entire mass converted into pure energy, with nothing left behind. No ash, no smoke, no waste. It is the most perfect and complete release of energy that physics permits. Thousands of times more potent than nuclear fusion, and billions of times more than any chemical fuel. A single gram of it could carry a spacecraft toward the stars. So why aren't we already building antimatter engines? Here is the problem. We can barely make the stuff at all. The great laboratories like CERN, smashing particles together at nearly the speed of light, produce antimatter only a few atoms at a time. In decades of work, everything humanity has ever created, every scrap of antimatter from every laboratory on Earth, adds up to roughly 10 billionths of a single gram. Not enough to boil a cup of tea. And the cost is almost beyond words. By one NASA estimate, producing a single gram of antimatter would run around $62 trillion. close to the value of everything the entire human species produces in a year, spent to make an amount you could not see without a microscope. A starship would need tons. Some believe that over centuries, entirely new methods could scale antimatter up from atoms to kilograms. Others suspect the gap is so vast, many billions-fold, that we may never close it. That argument isn't settled, but for now, the perfect fuel remains a substance we can dream about and barely touch. So other minds gave up on carrying fuel at all. Some imagined sails, vast, gossamer mirrors, thinner than a soap bubble and miles wide, pushed not by wind but by light itself, either from the sun or from titanic lasers built on a planetary scale, firing a beam across the void to drive the sail forward. And one idea was more elegant still. Back in 1960, the physicist Robert Bussard proposed a ship that would carry no fuel whatsoever. Instead, it would fly with an enormous magnetic net spread before it, scooping up the thin hydrogen drifting between the stars, funneling it into a fusion engine and burning it in flight. An engine that fed itself from the emptiness, that could, in theory, accelerate forever. It was a beautiful idea. And then the mathematics turned on it. In the 1980s, engineers Robert Zubrin and Dana Andrews ran the numbers carefully. To gather enough hydrogen from space, which is almost unimaginably empty, barely an atom or so in every cubic centimetre, the scoop would need a mouth around 10,000 square kilometres wide. That's an intake larger than the entire nation of Lebanon, dragging through the void. And here was the killing blow. That colossal magnetic net, sweeping up all those particles, would create more drag than the engine could ever turn into thrust. The very act of catching the fuel would slow the ship down more than burning it could speed it up. The self-fueling starship, it seemed, would break itself to a crawl. Not every researcher agrees the flaw dooms every possible design. The debate isn't fully closed, but the drag problem has haunted the ramjet ever since. And now we reach the cruelest twist in the whole endeavour, the one that every dreamer, at some point, forgets. Reaching the star is only half the journey. Think about it. If your ship is travelling at 1/10 of the speed of light, and it cannot brake, then reaching Alpha Centauri accomplishes nothing at all. You would simply flash through the system in a matter of hours and vanish out the other side, into an even deeper emptiness, unable ever to return. To actually arrive, to stop, costs roughly as much energy as it took to get moving in the first place. So you don't just have to solve the impossible problem of launching a world, you have to solve it twice. Once to leave, once to stop, unless, and here is where the story turns beautiful, you could find a way to stop for free. Remember the ramjet's fatal flaw, that its giant magnetic scoop created more drag than thrust. Zubrin and Andrews looked at that failure and saw something hidden inside it. If a magnetic field dragging through interstellar space slows a ship down, then why not use it on purpose, at the end, as a brake? They called it the magnetic sail. Picture a great loop of superconducting wire unfurled from the ship, carrying a current that generates a vast magnetic field around it. As the ship races through the thin soup of charged particles between the stars, that field pushes against them, and they push back, dragging on the ship, bleeding away its speed year after year. It's a parachute, but instead of catching air, it catches the near-nothingness of deep space itself, and lets the emptiness slowly haul the ship to rest. No fuel required. The very medium that makes interstellar travel so hard becomes the thing that finally stops you. So, at last, we have the shape of a solution, an engine to leave, a field to stop. Now comes the world itself, because a generation ship is not a rocket with rooms. It is a small, sealed planet, tens of kilometers long and weighing millions of tons. Let that mass land for a second. The Great Pyramid of Giza, the largest stone monument human beings have ever built, weighs somewhere around 6 million tons. A world ship might weigh as much, or more, which means the challenge is nothing less than taking the Great Pyramid itself, and hurling it toward another star at a fraction of the speed of light, then catching it gently at the far end. How do you even build a hull strong enough and heavy enough to protect a crew for 4 centuries? One idea is startling in its simplicity. Don't build the hull at all. Find an asteroid, a mountain of solid rock already drifting in space, hollow it out and live inside it. Meters of ancient stone wrapped around you would shield the crew from the radiation and the impacts of deep space far better than any metal shell we could manufacture. The ship would be older than the Earth, repurposed as a lifeboat, and inside that shell, you would build a landscape. The design borrows from a vision dreamed up in 1976 by the physicist Gerard O'Neill, the Great Rotating Cylinder. Imagine you could stand inside one. The interior is a valley curved into a tube several kilometers across and tens of kilometers long. There is farmland and rivers and clusters of homes. But when you look up, you don't see a ceiling. You see more land curving up and over your head until the far side of the world hangs above you like a second horizon in the sky. And beneath your feet, gravity, except it isn't gravity at all. The entire cylinder is slowly spinning, and that spin presses everything inside it outward against the inner wall, exactly the way water stays pinned to the bottom of a bucket swung in a circle, or the way a fast carnival ride pins you to its wall. Spin a world fast enough, and the outward press feels almost exactly like the tug of the earth beneath you. A gravity made entirely of motion. It's an astonishing piece of engineering. A breathing landscape, a curved sky, a false gravity, all sealed inside a spinning stone crossing the dark. But step back, and the sheer energy of this begins to crush the imagination. To accelerate a world of millions of tons up to even a fraction of light speed, and then to break it again, demands an amount of energy that rivals everything an entire civilization produces. Not for a moment, for years. We are talking about pouring the total output of humankind into a single vessel, twice over. This is why the most sober analysts keep arriving at the same quiet conclusion. A true crewed world ship is almost certainly not a thing of this century, and probably not the next. It waits somewhere in a future centuries beyond our own, when a civilization commands energy on a scale we can barely picture today. So imagine we get there. Imagine the engine is solved, and the brake, and the hull, and the spin, and the staggering energy. Imagine the Ark is finally fully built, a hollowed mountain with a landscape sealed inside, ready to sail. We would still be nowhere near done, because a metal shell with a river in it is not a home, it's a container, and the moment you seal thousands of living, breathing people inside it, cut off from Earth, from resupply, from every plant and animal and microbe that has ever kept us alive, you inherit a problem far more delicate than any engine. You have to keep them breathing for 400 years, with nothing coming in and nothing going out. And the first time we ever tried to build a sealed, living world like that, right here on Earth, it very nearly killed the people inside it. Step inside the finished Ark and go looking for a window. You will find them, but understand what they are and what they are not. Beyond that glass lies no air you can breathe, no water you can drink, no help that can ever arrive. The void outside offers the crew nothing but cold and radiation and silence. Every breath they take, every mouthful of water, every crumb of food must come from what the ship already carries, used, broken down to its pieces, and built back into something living again. Over and over, for 4 centuries. Scientists have a name for a machine like that. A closed ecological life support system. It means a world sealed so completely that nothing enters and nothing leaves, where the air, the water and the food must cycle in an unbroken loop forever. Here on Earth, our entire planet quietly does this for us, for free. Plants breathe out the oxygen we breathe in. Rain scrubs and returns our water. The soil digests our dead and feeds the next harvest. We never notice, because it has never once stopped. But could we build a smaller version? A living world in miniature, sealed under glass, that keeps human beings alive with no help from the planet outside. We tried, and it nearly broke us. In 1991, in the high desert north of Tucson, Arizona, 4 men and 4 women stepped through an airlock and sealed it behind them. They would not come out for 2 years. The place was called Biosphere 2, the name treating Earth itself as the original Biosphere 1, and inside its sprawling frame of glass and steel, engineers had built a tiny model of our whole living planet. Under that glass sprawled a miniature rainforest, a small ocean with a coral reef, a mangrove marsh, a savanna, a desert, and a patch of farmland, all packed into a space covering barely 3 acres, roughly the footprint of 2 football pitches, sealed off from the world. Living inside it, alongside the 8 people, were around 4,000 species of plants and animals, a whole ecosystem in a bottle. The idea was breathtaking. The crew would grow their own food, breathe air made by their own plants, drink their own recycled water, and prove that humanity could carry a slice of Earth with it, anywhere. For a little while, it seemed to work. Then something began to go wrong, something invisible. The oxygen started disappearing. Slowly, quietly, month after month, the amount of oxygen in the sealed air kept dropping, and for a long time, nobody could say where it was going. One of the crew, Mark Nelson, later described it plainly. The oxygen slipped away for 16 months, and no one knew why. Think about how unsettling that is. You are locked inside a sealed world, and the very air you depend on is draining away around you for reasons no one can find. The numbers tell the story. When they sealed the door, the air held the normal share of oxygen, just under 21%, the same as the air filling your lungs right now. Over the following months, it fell and fell, down to around 14.5%. That doesn't sound like much on paper, but that is the thinness of the air near the top of a 13,000-foot mountain, 4,000 meters up, where a simple flight of stairs leaves you gasping and your thoughts turn slow and foggy. The crew were breathless, exhausted. Some stopped breathing in their sleep. Their minds grew dull. They were, slowly and quietly, suffocating inside their own creation. So where had the oxygen gone? The answer came in 2 halves, and neither was obvious. The first half was alive. The rich soil they had packed in to grow their crops was teeming with microbes, countless tiny organisms that, like us, breathe in oxygen and breathe out carbon dioxide. And there were far more of them, eating far more oxygen than anyone had planned for. Invisible, uncountable, hungry. Normally that wouldn't matter, because plants would take that carbon dioxide and turn it back into oxygen, closing the loop. But here came the second half of the trap. The carbon dioxide never reached the plants. Instead, it was vanishing into the walls. The structure held a great deal of raw, uncured concrete, and curing concrete drinks carbon dioxide out of the air, locking it away inside the material as hard mineral, forever. So the oxygen wasn't truly gone. It had been pulled out of the air by the microbes, turned into carbon dioxide, and then swallowed by the concrete before any plant could breathe it back out. The building itself was eating their sky, a sealed world, undone by 2 things no one thought to watch: the life in the dirt and the chemistry of the walls. The suffocating air was only part of it. The crops struggled too. Light was weaker than expected, harvests came up short, and the 8 humans inside spent much of those 2 years genuinely hungry, thinning down month by month. And while the food they wanted refused to grow, other things thrived. The insects meant to pollinate their plants died off almost entirely, but cockroaches and ants bred explosively, sweeping through the tiny world in numbers that the crew could do nothing to stop. Here is the lesson that should stop us cold. This was a sealed world running for just 2 years, on Earth, monitored by a team of scientists standing safely on the outside, with the option to open the door at any moment, and it very nearly failed. One hidden imbalance, invisible until it was almost too late, came close to defeating a model of our own planet in under 24 months. Now take that fragility and stretch it across 400 years, in deep space, with no door, with no outside, with no one left to open it. But we did not stop trying, and the science has come a long way since that glass world in the desert. The most important idea to come out of it all is deceptively simple. If you want to keep a crew breathing forever, don't rely on a whole tangled ecosystem you can barely predict. Instead, hand the job to the smallest, most reliable workers in all of biology. Microbes. Algae. The Soviet Union saw this early. Deep in Siberia, at an institute in Krasnoyarsk, researchers built a sealed facility called BIOS 3, a room of about 300 cubic meters, no bigger than a modest house inside, and using tanks of green algae to renew the air, it kept small crews of 2 or 3 people breathing and supplied for months at a time, recycling something like 95% of their atmosphere. A living world, small enough to fit in a basement, that mostly worked. Europe went further still. The European Space Agency, ESA, has spent decades on a project called Melissa, its name standing for a micro-ecological life support system alternative, and its design is elegant. Picture a chain of connected tanks, each one a small living reactor, each filled with a different colony of microbes or algae, each doing one specific job. One breaks down human waste, the next processes what the first produced, the next cleans the water, and at the heart of it, tanks of algae drink in carbon dioxide and pour out fresh oxygen, the way a lake breathes, while doubling as something the crew can actually eat. That is the quiet genius of it. The same algae that make your air can also become your food, because food is the part you cannot cheat. The obvious plan would be to simply pack enough supplies for the journey, but a 4-century voyage makes that impossible, and not only because of the sheer quantity. Stored food doesn't just run out, it decays. Over years and decades, the vitamins inside dried and preserved food slowly break down and lose their power, until what's left may fill a stomach, but can no longer keep a body healthy. Pack a warehouse of food for a 400-year trip, and long before you arrive, it becomes a warehouse of poison-free but lifeless dust. So there is only one real answer. The crew has to grow their food, fresh, aboard the ship, every year, without a single break, for the entire voyage. Which raises a very practical question. How much farmland does it take to feed a crew forever? An astrophysicist named Frédéric Marin working in France actually ran the numbers. Using a detailed computer model, he calculated the calories a realistic crew would burn, accounting for the tall and the short, the young and the old, the pregnant and the aging, and then worked out how much growing space it would take to supply every one of those calories, indefinitely. For a crew of 500 people, eating a balanced, varied diet, the answer was about 0.45 square kilometres of farmland. That is roughly 60 football pitches of crops, orchards, grain, vegetables and livestock, all somehow packed inside a spinning vessel and lit by artificial suns. And that is the farmland alone. Once you add the homes, the machines, the engines and everything else Marin noted, the ship would have to be at least twice as large again. And we know, on a small scale, that growing food in a sealed box can work. NASA once ran a closed chamber that grew crops on just 20 square meters, about the size of a small bedroom floor, continuously for more than 1,200 days, over 3 years without stopping. So, the pieces exist. But here is where the confidence cracks. We have kept crews breathing for months. We have grown crops for a few years. But whether any closed, living ecosystem can stay balanced and stable for centuries, that has never once been demonstrated. Not on Earth, not anywhere. It remains honestly unproven. And 2 quiet dangers lurk inside that uncertainty. The first is chemical. In a closed loop, the nutrients that feed the crops, the nitrogen, the minerals, the building blocks of life, get used and released and used again, cycle after cycle. But with each turn, a little can slip into forms that plants can no longer absorb, locked chemically into dead ends, still present but useless. Slowly, invisibly, the soil of the ship could starve even as it stays full. The second danger is sharper and faster. A single crop disease, one blight, one fungus, one virus that finds its way into the ship's few strains of plants, and with no wild backup, no neighbouring farm, no new seed from outside, it could sweep through the entire food supply and starve everyone aboard before the next harvest. On Earth, a failed crop is a hardship. On the Ark, it is extinction. And underneath the living systems runs the machine, and it must never, ever stop. The reliability this demands is beyond anything humanity has ever built. Consider that a nuclear power plant, one of the most carefully engineered machines on Earth, is designed to run perhaps 40 or 60 years before it needs major rebuilding. The Ark has to run for centuries. Every pump, every seal, every wire, every panel across a vessel with millions upon millions of parts. And somewhere always, something is wearing out, cracking, failing. There is no factory to call, no spare part to order, no delivery that will ever come. So the ship must carry within itself the ability to rebuild almost anything, the raw materials, the tools, the knowledge, and its people must find and fix each failure as it comes, endlessly, forever. Every critical system needs a backup, and because the backup can fail too, the backup needs a backup of its own, a city that is also its own factory, its own repair crew, and its own emergency service, for 400 years, with no outside world to lean on. Master all of it, the air, the water, the food, the endless repairs, and the machine can keep human bodies alive across the dark. And yet, for all of this staggering engineering, we have been quietly circling a harder truth. The fragile part of the Ark was never the oxygen, or the crops, or the failing parts. Those in time we might learn to master. The truly fragile part, the part no reactor can stabilize and no algae tank can renew, was always the people. Because now the machine is finished, the world is sealed, the farms are planted, the loops are closed, the backups have backups. Everything is ready, and it is time at last for the founders to say goodbye to the Earth and to become the only human beings who will ever remember it. The day of departure finally comes, and a small group of people gather to do something no human being has ever done, to say goodbye to the Earth, knowing that the word has never once carried this much weight. Not goodbye for a year, not goodbye for a lifetime, goodbye forever. And not only for themselves, but for every child, every grandchild, every descendant they will ever have. We can give them a name, Generation Zero, the Founders, and they carry a burden no one who comes after them will ever fully share, because they are the only human beings who will ever ride that ship while still remembering what a real sky looks like. The only ones who will board it already, knowing the smell of rain, the sound of an ocean, the feel of wind that no machine ever made. They volunteer for this. That is the part that stops you. They step aboard with open eyes, understanding that they will grow old inside that vessel and die inside it, somewhere in the black gulf between two stars, never arriving, never returning, giving their entire lives to a destination their great-great-grandchildren might one day reach. They are planting something they will never live to see grow. Then the engines light. Whatever we finally built to move that world, the nuclear fire, the fusion drive, the magnetic sail furled and waiting, it wakes, and the Ark begins to move. Not with a violent leap, with a slow, patient, unstoppable push. Because you cannot fling a world up to speed the way you launch a rocket. Push too hard, and everything inside, the people, the farms, the oceans, would be crushed against the walls. So the acceleration is gentle, barely a nudge, And that nudge continues day after day, year after year, for a very long time. Slowly, the ship climbs toward its cruising speed, somewhere around 1% of the speed of light. That number sounds small. It is not. 1% of light speed is fast enough to carry you from New York to London in about 2 seconds. The entire Atlantic Ocean crossed between 2 heartbeats. And yet, against the 4 light years ahead, even that blistering pace is barely a crawl. This is the cruel arithmetic we met at the very start, made real at last. The founders feel none of it. Inside, the floor holds steady, the false gravity spins on, and the only sign of their monstrous speed is what happens when they look back. Behind the ship, the Earth begins to shrink. For a while, it stays a recognizable world, blue, alive, wrapped in cloud. Then it dwindles to a bright point among the stars, and then it becomes something smaller still. We already know exactly what that looks like, because we have seen it. In 1990, a small spacecraft called Voyager 1 turned its camera around from 6 billion kilometers away, about 3.7 billion miles, and photographed the Earth one final time. And in that image, our entire planet, every person who has ever lived, every war, every love, every ocean, was reduced to less than a single dot on the screen, barely 1/10 of 1 pixel, a pale blue speck caught by chance in a stray beam of sunlight. The astronomer Carl Sagan, who fought to have that picture taken, called it a mote of dust suspended in a sunbeam. Now imagine that same view, but you are not a camera drifting away on autopilot. You are a person, standing at a window, watching your home become that speck, and then watching the speck itself dissolve into the background of stars until you cannot find it anymore, until there is no direction you can point and say, that way is home. For Generation Zero, that moment comes, and it never uncomes. And yet, here is something that almost no one expects. Even after Earth has vanished, the ship has not truly left the sun behind, because our sun's realm does not end at the last planet. Far, far beyond Neptune, beyond even Pluto, the sun is surrounded by a vast, faint shell of frozen comets called the Oort cloud, trillions of icy bodies left over from the birth of the solar system, drifting in the deep cold, and this shell is almost unimaginably huge. By NASA's estimate, its outer edge lies around 100,000 times farther from the sun than the Earth is. Sunlight, which reaches your face in about 8 minutes, would take more than a year to cross to that distant boundary. That places the edge of the sun's cometary cloud well over 1/3 of the way to Proxima itself, and by some estimates, nearly halfway there. So think about what that means for the ship. Cruising at 1% of light speed, the Ark would need well over a century, more than 1/3 of its entire 400-year voyage, simply to clear the outermost fringe of the sun's own comets. For the first 150 years or so, generations would live and die aboard a ship that is, technically, still inside the solar system, still, faintly, in the sun's shadow. And then, at last, they cross the final threshold, and everything changes. Beyond the Oort cloud lies true interstellar space, and it is emptier and darker than almost anyone imagines. Here, the sun is just another star, one bright point among thousands, no longer warming anything, no longer holding anything. The nearest star ahead is still years of travel away. In every direction there is nothing but scattered pinpricks of ancient light and an immensity of cold, black vacuum in between. If you could stand at that window now, in the deep between the stars, you would see no destination and no origin, just the ship's own quiet lights, and beyond the glass, a darkness so complete and so vast that the human mind was simply never built to hold it. This is the ocean the founders chose to cross, and they will never see the far shore. Something else happens out here too, something stranger and quieter. Time itself begins to bend. Einstein showed us, more than a century ago, that the faster you move through space, the slower your clock ticks compared to those you left behind. At everyday speeds, the effect is far too tiny to notice, but it is always there. And aboard a ship moving at a real fraction of light speed, it becomes genuinely measurable. So you might wonder, could the crew use this to cheat the journey? Could time slow down enough aboard the Ark to spare them the centuries? The honest answer is no. At 1% of light speed, the effect is real but small. Across the entire 400-year voyage, the ship's clocks would fall behind Earth's by only about a week. 4 centuries of flight, and the calendar aboard is off by a matter of days. Even in a faster design, the gap might stretch to a couple of months, no more. There is no escaping time out here. The founders will age exactly as they would have on Earth. Their bodies will not be spared a single day. And then comes a moment that no one aboard can see, but everyone aboard can feel. A line, somewhere in the dark, that once crossed can never be uncrossed. Before that point, turning back is at least imaginable. The ship could, in principle, slow, reverse, and limp home. But past a certain distance and a certain speed, that option quietly dies. There is not enough fuel to stop and return. There is not enough life left in any founder to survive a second voyage. From that instant on, the mission has exactly one direction: forward. Always, only forward. After the point of no return, home is no longer a place you can go. It is only a place you came from, which forces the founders to do something profound and a little haunting. They have to build a society designed to outlive every single one of them. Think about that. They are writing the rules for a civilization made almost entirely of people who do not exist yet. People who will be born, live, and die aboard, whom the founders will never meet. Who decides how many children may be born and when? Who leads? And how is that leader chosen 10 generations from now? What happens when the ship's few hundred people disagree and no one can ever walk away? Every question we've spent thousands of years answering on a whole planet, with room to move, to leave, to start again somewhere else, must now be answered inside a sealed vessel where leaving is death. The founders write those first laws blind. For descendants they can only imagine, facing problems no human society has ever faced. And then, into that strange new world, the future actually arrives. The first child is born aboard the ship, and this child is something genuinely new in the story of our species, because this is a human being born into a universe made entirely of metal and recycled air and artificial light. A child who will never stand on a shore, never climb a mountain, never feel real rain, or look up at an open sky and see clouds or a moon or a sunrise that a star actually made. To this child, the whole of existence is the inside of the ship. Earth is not a memory. It is a story, a thing the old people describe, like a fairy tale of a blue world with an ocean you could not see across. And not long after that first cry, the ship faces the other side of life, the first death. A founder passes, one of the originals, one of the ones who remembered, and their body is committed not to soil, but to the void outside, released into the same dark the ship is crossing, the first grave in interstellar space. And this is the quiet, aching heart of the whole endeavor. With every birth and every death, the Earth slips a little further out of reach, not in distance, but in memory. The founders knew it as home. Their children know it only as their parents' home. Their grandchildren know it as a word in a lesson, and somewhere down the line, a generation is born for whom Earth is barely more real than a myth, a thing that may as well never have existed, because no one alive has ever seen it. The memory of our entire world fades, generation by generation, from lived experience into legend. Generation 0 grows old carrying that fading light. They teach their children everything: how to run the ship, how to grow the food, how to fix what breaks, and who they all are, and why they are out here in the dark at all. And their children will one day teach their children the same. A chain of hands passing the mission forward, link by fragile link. Then, one by one, the founders die. They die having given their whole lives, every single year of them, to a voyage whose ending they were never going to witness. They will never see Proxima grow from a dim red star into a sun. They will never know whether the mission succeeds or fails. They simply spent themselves completely so that someone unimaginably far in the future might arrive. The ship sails on, carrying their promise into the centuries. But as Generation Zero passes into memory, and the children of the ship begin having children of their own, a new threat quietly stirs. And this one cannot be fixed with any engine, or any law, or any farm, because a starship does not carry a whole species. It carries only a few hundred people, a tiny closed pool of human beings, cut off from every other human who has ever lived. And a pool that's small has a hidden flaw written into its very cells. Send too few ancestors into the dark, and something begins to go wrong deep inside the bloodline itself, slowly, invisibly, generation after generation. The next fight for survival will not be fought against the vacuum, or the cold, or the machine. It will be fought inside human DNA. The deadliest threat aboard the Ark was never the vacuum or the radiation or the failing machines. It was chosen, deliberately, before the ship ever left the ground. And once chosen, it could never be taken back. That threat is a single number, the size of the crew, because a generation ship does not carry humanity. It carries a sample of humanity, a few hundred or a few thousand, sealed away from the 8 billion they left behind. And the exact size of that sample quietly decides whether their descendants arrive healthy or arrive doomed. Here is the trap, and it closes from both sides at once. Send too few people, and you invite a slow poison. In a tiny population, cut off from all others, everyone eventually becomes everyone else's distant cousin. Over generations, close relatives inevitably have children together, not by choice, but because there is simply no one else. And that quietly concentrates the hidden flaws buried in human DNA, until disease and weakness begin to surface in child after child. The bloodline itself starts to fail. So the obvious answer is, send more people, send thousands, send tens of thousands, except that every extra body is more mass, more food, more water, more air, more living space, all of which must be hauled up to a fraction of light speed and then braked again at the far end. We already saw what moving a single small world costs. Now multiply it. Each additional passenger makes the ship heavier, hungrier, and more impossible to launch. So how many humans does it actually take to safely cross the stars? You would think, after decades of study, scientists would have settled on an answer. They have not. And what makes this so fascinating is that they don't just disagree by a little. Their answers span more than 2 orders of magnitude, from fewer than 100 people to more than 40,000. That is not a rounding difference. That is one group of serious researchers saying you need a small village and another saying you need a small city. On the single most fundamental question of the entire mission, how many people to bring, the experts differ by a factor of hundreds. Let's walk through how such a gulf is even possible, because each answer is built on solid reasoning. They simply start from different fears. At the low end stands the work of John Moore, an anthropologist at the University of Florida. He looked at how human beings actually lived for most of our history, in small, tight-knit clans and tribes, bands of a few hundred that survived for thousands of years by following strict rules about who could marry whom. Applying that logic to the stars, Moore concluded that a starting crew of only around 150 people could work, provided they carefully avoided pairing close relatives, a number small enough to fit inside a single village hall. Enough, he argued, to carry a healthy bloodline across a voyage of many centuries. Then the astrophysicist Frederick Moran pushed the number even lower, and did it with something more powerful than intuition. Working with the particle physicist Camille Belluffy, Moran built a computer program called Heritage. And Heritage did something remarkable. It simulated an entire voyage, person by person, year by year. Every birth, every death, every pairing, every pregnancy, every accident, every stroke of bad luck, run over and over across thousands of imaginary journeys to see how many crews survived and how many quietly went extinct. And the answer his simulations landed on was startlingly small. Under a strict set of rules, a bare minimum of 98 people could sustain a healthy population across a multi-generational voyage. Think about that. Fewer than 100 human beings, the number you might pass in a single busy grocery store, as the seed of an entire world. But that word, strict, is doing an enormous amount of work. Because Marin's 98 only survive if the ship controls something most of us consider deeply private. We'll come back to that. First, the other extreme. Because another expert looked at the very same problem and arrived at an answer nearly 400 times larger. Cameron Smith, an anthropologist at Portland State University, ran his own detailed models and concluded that a founding crew should number not dozens, but tens of thousands. His floor was around 10,000 people, and to be genuinely safe, he argued, you would want closer to 40,000, of whom perhaps 23,000 would be of childbearing age. 40,000 people. That is not a village or a town. That is the population of a small city, launched whole into the dark. So who is right? The village or the city? And how can careful scientists, looking at identical biology, disagree so violently? The answer is that they are not really arguing about genetics. They are arguing about how much to fear disaster. Marin and Moore ask a lean question. What is the smallest crew that can stay genetically healthy if everything is carefully managed and nothing catastrophic happens? Their goal is efficiency, the least mass, the lightest ship, the mission that can actually be built and launched. Smith asks a darker one. What happens when something does go wrong? A plague, a disaster, a generation struck by tragedy. On Earth, a small population that suffers a catastrophe can be replenished from the outside. There are always other people, somewhere, over the next hill. But a starship has no next hill. It is a single, closed population with nowhere to run and no one to call. And so, Smith builds in an enormous margin, a crowd so large that even a genetic catastrophe couldn't wipe out its diversity. One side optimizes for the best case, the other braces for the worst. Both are being entirely reasonable, and that is exactly why the debate remains unsettled. It is not a fight about the math, but about how much safety a civilization owes to people who cannot yet speak for themselves. To feel why any of this matters, you have to meet the three quiet forces that stalk a small, isolated population. They are invisible, they are patient, and across enough generations, they are lethal. The first is genetic drift. In any population, traits get passed down a little randomly from one generation to the next. In a huge population, that randomness averages out and nothing much changes. But in a tiny one, pure chance can erase things. Picture a jar holding just a few coloured marbles, and each generation you blindly scoop a handful to carry forward. By sheer luck, an entire colour can simply vanish. Not because it was bad, but because no one happened to grab it. In a giant barrel of marbles, the colours stay balanced forever. In a small jar, they drift and disappear. The second is mutation. Every generation, tiny copying errors creep into human DNA. That is normal and constant. In a large population, natural selection quietly weeds the harmful ones out. But in a small, sheltered crew, those errors have nowhere to be diluted. They accumulate generation after generation, like a document photocopied from a photocopy from a photocopy, until the flaws pile up and the text begins to blur. And the third is the founder effect, perhaps the most haunting of all. Whatever genes those first few hundred settlers happen to carry become the entire genetic inheritance of everyone who ever comes after. Every quirk, every hidden weakness, every random flaw in that small founding group is stamped onto the whole future population, permanently. If you built a new human race from 5 people, the whole species forever after would carry only their traits, their accents, their errors. And we are not guessing about any of this. We can see it today in real human populations. Consider what happened in South Africa. Much of the country's Afrikaner population descends from a small band of settlers who arrived centuries ago, and among them was a single couple, married in the late 1600s, who happened to carry the gene for a rare disorder called porphyria, that one hidden flaw riding in the blood of 2 people, spread down through the generations until it became strikingly common in their descendants. Thousands of people today carrying a condition that traces back to a single 17th century marriage. A whole population marked by the genes of a couple most of them have never heard of. That is the founder effect, written into living human beings. Certain communities descended from just a small handful of ancestors show noticeably higher rates of specific inherited diseases, conditions like Tay-Sachs or cystic fibrosis, precisely because their gene pool traces back to so few. The narrow inheritance is real and measurable and written into people's health right now. Now shrink that founding group down to a few hundred, seal it inside a metal hull, and let it run not for a few generations, but for 16 or more. That is the gamble a generation ship makes with its own blood, which brings us back to Marin's strict rules and to something genuinely unsettling. For a crew as small as 98 to survive, the simulations demand tight control over who has children and with whom and exactly when. The ship cannot simply let people fall in love and start families as they please. It must actively manage the gene pool, deciding which pairings are safe, spacing out births, ensuring each generation reproduces at the right size and the right moment to keep the bloodline healthy. The window for having children becomes something the whole society must ration and schedule, carefully, for centuries without pause. And the fragility runs deep. A single generation that fails to reproduce enough, one cohort that has too few children, for any reason at all, could send the whole population into a slow spiral it can never climb back out of. One barren generation, and the colony quietly begins to die. So now the 2 halves of the mission are locked against each other, and there is no clean way to reconcile them. Genetics pushes the number up. The safer you want the bloodline, the more people you must bring, pushing towards Smith's tens of thousands. But engineering pushes the number down. Every one of those people is mass, and mass is the one thing the rocket equation punishes without mercy. A ship for 40,000 is a monster many times heavier than a ship for a few hundred. Vastly more energy to launch, vastly more to stop, vastly more that can break along the way. The genetic answer and the engineering budget are at war, and that war has no obvious winner. Faced with that deadlock, scientists have proposed clever ways to cheat it. One idea is to leave most of your gene pool in a freezer. Instead of hauling 40,000 living, breathing, eating people, you carry a few hundred, plus a vast bank of frozen sperm, eggs, and embryos. A genetic library, sitting cold and weightless in storage, ready to introduce fresh diversity into the population whenever the bloodline starts to narrow. All the variety of a city, at a fraction of the mass. But even that quiet solution hides a catch. Frozen cells are not truly timeless. Across centuries, the faint, ceaseless radiation of deep space seeps into everything aboard, and a genetic library, sitting in storage for 400 years, could slowly accumulate damage of its own, the very diversity meant to save the crew degrading in the dark. And there is a human problem too. Who, generations from now, decides when to open that vault? Who chooses which frozen strangers become the parents of the next child? The freezer solves a genetic problem by handing the crew a profound moral one. Another idea goes further, and stranger still, to reach directly into the crew's DNA and engineer it, to edit the human genome itself so it resists the mutations and the decay that a long voyage would otherwise inflict, redesigning our own biology to survive a trip our bodies were never built for. It might work, but every edit is a bet placed on incomplete knowledge, a change whose full consequences might not surface for generations, by which point there is no way to take it back. Both ideas might save the mission. Both also carry consequences we can barely predict. Because here is the quiet, profound truth underneath all of it. Even if everything goes right, even if the bloodline stays perfectly healthy, the people who step off that ship will not be the same people who boarded it. And not only because centuries have passed. Across 400 years, 16 generations or more will be born and die aboard. As many generations as separate you from your own ancestors, back in the age of Shakespeare. And over that many generations, genetic drift alone, that slow, random reshuffling, will gently reshape the population. Traits will fade, others will spread. The crew will slowly become genetically distinct from the humanity they left behind. And there may be something even stranger at work. Their bodies will be adapting, subtly, across the generations, not to any waiting planet, but to the ship itself, to its gravity, its light, its air, its enclosed and unchanging world. They may arrive at Proxima superbly suited to life aboard a starship, and quietly unsuited to the open world they were sent to settle. Solve this mathematics of blood, and the colony can physically survive the crossing. Fail it, and the ark becomes something unbearable, a sealed coffin drifting on toward a star, carrying a bloodline already doomed before it arrives. And yet, suppose we get all of it right. Suppose the crew size is perfect, the gene pool stays rich, the births are timed, the bloodline holds strong for 4 centuries. Even then, we have only kept the body alive, because a human being is not only a genome. A person is also a mind, with memories and meaning, and a need for a world that makes sense. And a healthy body tells you nothing about whether the spirit inside it can endure being born, living, and dying inside a metal shell that never once opens a door. The next threat cannot be measured in genes. It is measured in generations of confinement, in what happens to the human mind when it is sealed in the dark for longer than anyone ever agreed to. The next threat has no body. You cannot shield against it, or repair it, or breed it out of the bloodline. It grows in the one place the ship can never armor. The human mind. Generations deep into the voyage, something strange begins to take hold. Because by now, the people aboard have never known anything else. They were born in the metal. They will die in the metal. To them, the ship is not a vessel carrying them somewhere. The ship is simply the world, the only world, the way the ground beneath your feet is just the ground. And Earth has become a legend, a story the oldest among them half remember hearing from someone who half remembered it themselves. The bright blue world, the open sky, the ocean, as real to them as a fairy tale. And the destination, that far red star they are still centuries from reaching, is a myth of a different kind, a promise made by the dead to people not yet born. So what does that do to a human being? To live an entire life sealed inside a machine, with no sky, no horizon, no escape? We actually have the beginnings of an answer. And it is not reassuring, because we have run the experiment, in miniature, here on Earth. Consider what happened in a facility in Moscow. Working with the European Space Agency, Russia's Institute for Biomedical Problems sealed 6 volunteers inside a mock spacecraft and left them there, cut off from the world, for 520 days, nearly a year and a half, locked in a space about the size of a modest apartment to simulate the psychological toll of a journey to Mars. They called it Mars 500. And these were not random people. They were carefully chosen, highly trained, mentally screened, and supported by a team monitoring them the whole time. About the most resilient crew you could assemble. Even so, the strain showed. As the months dragged on, the crew grew quietly more sluggish, moving less, sleeping and resting more, slowly winding down like a clock no one was rewinding. Most of them suffered disturbed sleep and disrupted body clocks, drifting out of sync with the day and night they could no longer see. Positive feelings dimmed, and the individuals diverged sharply. Some coped remarkably well, while at least one withdrew into something that looked like depression, retreating inward as the walls stayed close. But the researchers noticed something else too, something that should worry anyone planning a voyage of centuries. Scientists who study confinement have long observed a pattern they call the third quarter phenomenon. It works like this. For a while, the sheer novelty and challenge carries people through, but somewhere past the halfway mark, once the excitement has worn off and yet an enormous stretch of time still lies ahead, mood tends to sag, tension tends to rise, and small irritations start to fester. And here is the unsettling part. That dip seems tied, not to how much time has actually passed, but to how much still remains. It is the feeling of being past the middle, with the finish line still impossibly far. Now think about what the halfway mark means on a 400-year voyage. It means roughly 200 years in, a point no single person aboard will ever personally cross, because no one lives that long. The entire crew, for generation after generation, would be living somewhere inside that long, sagging middle stretch, with the destination still a lifetime or more beyond reach. A year and a half nearly wore down the best of us, and a year and a half is nothing. More recently, NASA ran its own version, and it is still running them now. In a hangar in Houston, the space agency built a Mars habitat out of a 3D printer, called it Mars Dune Alpha, and sealed 4 volunteers inside for 378 days, a full year and then some. 1,700 square feet of enclosed space, about 160 square meters, roughly the floor of a large family home, and no way out. This is the CHAPIA program, and its entire purpose is to learn what a year of true isolation does to human beings before we ever send them to another planet. The crew grew their own vegetables, they ran simulated Mars walks, and, crucially, they lived with a delay. Every message to the outside was made to lag by up to 22 minutes each way, mimicking the crawl of radio signals across the Gulf to Mars. Say something, and the answer cannot come back for the better part of an hour. Now hold that thought against the arc, because on a ship crossing to Alpha Centauri, that delay does not stay at 22 minutes. It grows and grows until a single message home takes over 4 years to arrive and 4 more years to be answered. Long before that, the crew simply stops speaking to Earth at all. Why send words into a silence that will outlive you? They are alone in a way no isolated crew on Earth has ever truly been. And here is the leap that changes everything. Every study we have, every sealed habitat, every Antarctic winter, every simulated Mars, measures months, or at most a year or two, endured by volunteers who chose to be there and knew the door would open. Now stretch that across a dozen generations of people who never chose any of it, and for whom the door never opens at all. Across that many lifetimes, something begins to drift that we rarely think of as fragile. Culture itself. Language does not sit still, and we have proof of this, written across our own history. 2,000 years ago, people across a vast stretch of Europe all spoke one language, Latin. But cut those populations off from one another, let them drift apart over the centuries, and that single tongue slowly fractured into French, Spanish, Italian, Portuguese, and Romanian, languages so different that their speakers can no longer understand one another at all. No one decided this. It simply happened, word by word, generation by generation. Now seal a few hundred people inside a metal hull, away from every other human on Earth, and run that same process forward. After a dozen generations, the crew may be speaking something their founders would struggle to follow. 12 generations is further back than most of us can name a single ancestor. And across that span, beliefs mutate, customs harden into rituals whose reasons are long forgotten, and the stories the founders told get retold, embellished, and slowly reshaped into something else entirely. And the most dangerous thing that can drift is knowledge. Think about how much of what keeps that ship alive lives only inside human heads. How to repair the reactor, how to balance the ecosystem, why a certain valve must never be opened, what the mission even is. On Earth, if one person forgets, a library remembers, a specialist remembers, the whole internet remembers. On the Ark, the chain of knowing is only ever a few minds wide. So picture that chain and imagine a single link in it breaking. One engineer who understood the deepest workings of the life support system dies a little sooner than expected, before she finished teaching the one apprentice who was meant to replace her. The apprentice knows most of it, not all of it. He teaches his own students most of what he knows, a little less again, and 3 generations later, no one aboard truly understands why the system does what it does. They can still push the buttons, they have simply forgotten the reasons. And the day something goes wrong in a way the buttons don't cover, there is no one left alive who knows how to save them. Vital understanding can decay from hard fact into vague ritual, and from ritual into nothing at all. The crew could forget how their own world works. Science fiction saw this danger long before the scientists did, and one story took it to its unforgettable extreme. In 1941, the writer Robert Heinlein imagined a generation ship, later collected into a book called Orphans of the Sky, where something has gone catastrophically wrong across the centuries. The crew has forgotten the mission. Worse, they have forgotten they are even on a ship at all. To them, the vessel is not a vessel. It is the entire universe, the whole of reality, from wall to wall. And anyone who dares suggest that the ship is a thing moving through some larger space outside is treated not as a visionary, but as a heretic. For a moment, place yourself inside that world. Imagine you were born there, in that later, forgotten age. The curved metal wall overhead is simply the sky. You have never conceived of anything beyond it. The low hum in the deck is the sound the world has always made. When the elders speak of a place called Earth, or a bright star the ancestors were sailing toward, you nod politely at the old myths, the way we nod at stories of gods and monsters. To you, there is no outside. The idea is not frightening. It is nonsense. You are living inside the whole of everything, and everything is a few hundred meters wide. It is fiction, but it is fiction built on a terrifyingly real possibility. Strip away the memory of where you came from and where you are going. Keep people sealed in a metal world long enough, and the mission, the entire reason for their existence, could dissolve into legend. A crew still alive, still breathing, still crossing the void, with no idea anymore that they are going anywhere at all. And a crew like that raises a colder question. Who, exactly, is in charge? On Earth, if you despise your government, you can, in the last resort, leave, cross a border, walk away. On the Ark, there is no away, no border, no frontier, no somewhere else. Everyone is locked in the same metal room, forever, with the same few hundred people. That single fact turns governance into a matter of life and death, because a rebellion aboard a starship is nothing like a rebellion on Earth. One furious generation, one act of sabotage against the reactor, or the air, or the farms, and everyone dies, the rebels included, and every unborn generation with them. The stakes of every political dispute are total. There is no room to be wrong, and nowhere to run when you are. So some who study this arrive at a grim answer, that to prevent that lethal chaos, a generation ship might have to become something rigid and tightly controlled, a society that cannot afford dissent, cannot afford disorder, cannot afford freedom as we understand it, a floating dictatorship, ruling not out of cruelty, but out of the sheer arithmetic of survival. And yet, the opposite danger is just as real. Squeeze a crew hard enough, for long enough, and eventually the pressure finds a crack, and the breaking kills everyone. The ship is caught between two ways to die: too much freedom and too little. Even boredom becomes a genuine threat, not a mild annoyance, a danger. Stretch the sameness of an unchanging metal world across centuries, generation after generation, with nowhere new to go and nothing new to see, and the slow erosion of purpose can become as deadly, over time, as any radiation. A mind with nothing to reach for is a mind that can quietly come apart, and a whole society of them can take the ship down with it. But underneath every one of these dangers lies a deeper one, a question that shadows the entire voyage, from the first day to the last. The founders chose this. That is the crucial thing. Generation Zero volunteered, with open eyes, understanding exactly what they were giving up and why. It was their life, and their choice to spend it. But their children never chose, and their children's children never chose. Every human being born aboard that ship after the founders is born into a sealed world, a fixed mission, and a life of profound confinement, sentenced to it, in a sense, before they ever drew breath. They inherit not just the ship, but the decision, a choice made by people centuries dead that they can never unmake and never refuse. So here is the question, and it is not a comfortable one. Is it ethical to condemn generations of unborn people to a life they never agreed to decide on their behalf, before they exist, that they will live and die inside a flying container, bound to a purpose chosen by strangers in the distant past? The writer, Kim Stanley Robinson, built an entire novel, Aurora, published in 2015, around exactly this wound. His characters, deep into their own generation ship's voyage, come to rage at the trap they were born into. Their whole lives spent and risked and possibly lost for a mission they never had any say in. Robinson has argued, seriously and pessimistically, that this may be one of the deepest problems with the entire idea. Philosophers have a name for it, the problem of intergenerational consent, and the debate it opens has no easy floor to stand on. On one side, the argument is stark: to create people specifically to live imprisoned in a machine with no exit and no choice, carrying enormous risk they never accepted, is, some say, a profound moral wrong, a crime committed against the unborn, dressed up as an adventure. However noble the goal, you are using future human beings as a means to reach it, spending their freedom to buy your dream. But there is another answer, and it is not so easily dismissed, because no child, anywhere, in all of history, has ever consented to being born. Not one. Every one of us was brought into existence by a decision we had no part in, into a time, a place, a body, and a set of circumstances we never chose. Parents on Earth make life-defining choices for children who cannot yet agree: where they will live, what they will believe, what dangers they will face. A child born on the Ark, this argument goes, is not fundamentally different from a child born into any hard circumstance on Earth. To be born is always to inherit a world you did not pick. Both arguments are serious. Both are honest, and the tension between them refuses to resolve, because it is not really a question about starships at all. It is a question about what we owe to the people who come after us, asked in the most extreme form imaginable. The morality of the whole endeavour in the end stays exactly as fragile as its recycled air, and so the Ark carries them onward, a small, sealed civilization, holding its memory and its meaning and its fragile piece together against the slow pressure of the centuries. The crew may endure all of it. They may hold the culture, keep the knowledge, govern themselves with wisdom, and carry the mission whole across the dark. Or the whole thing may quietly come apart, and the ship may drift on as a slow, unfolding tragedy, alive but lost. But whether their spirits hold or shatter, the universe outside the hull has been waiting this entire time, patient, indifferent, and now, far from any home, far past the point of any rescue, the voyage runs headlong into its single greatest physical crisis, a gauntlet of radiation and impact, and one shattering piece of news from up ahead that could make the entire journey meaningless. The dark, it turns out, was never empty, and it does not forgive. Deep in interstellar space, far past any hope of rescue, the Ark meets a set of enemies that feel nothing, negotiate nothing, and stop for no one. And the first of them is invisible, constant, and everywhere. The void is soaked in cosmic rays. Now, the name is misleading. These are not rays of light at all. They are particles, the naked cores of atoms, stripped bare and flung across the galaxy at almost the speed of light, many of them hurled outward by the death explosions of ancient stars. Atomic bullets, fired from supernovae that detonated before the Earth was born, still racing through the dark tens of thousands of years later. And these bullets do not politely bounce off a hull. Each one can punch straight through meters of solid metal and straight through a human body. When one tears through you, it rips a microscopic tunnel through whatever it hits, shattering the delicate strands of DNA inside your cells. One such strike might be repaired, but out here, they never stop coming. Year after year, decade after decade, they seed the slow damage that becomes cancer and the mutations that ripple into the next generation. So why don't we simply wrap the crew in something thick and heavy? On Earth, that is exactly what protects us. We rarely think about it, but our planet fights this same storm for us every second of our lives. Earth's magnetic field deflects the charged particles, and the blanket of our atmosphere soaks up the rest. The air above your head does the shielding work of roughly 10 meters of water, an invisible wall we were all born beneath and never notice. The Ark carries none of that. No planet-sized magnet, no ocean of air. It sails into the storm naked. The obvious answer is to build a thick metal hull and hide behind it. But here the universe lays a genuinely cruel trap, one that turns your armor against you. Because when one of those atomic bullets slams into a heavy metal shield, it does not simply stop. It shatters the atoms of the metal itself and blasts out a spray of new particles, a shower of secondary radiation, spilling out the inside of the shield and into the very space you are trying to protect. Physicists call this process spallation, and it means that past a certain thickness, adding more metal makes the radiation worse, not better. Your shield becomes a second gun, firing inward. Think of it like a shotgun blast hitting a pane of glass. The single incoming pellet is stopped, but the glass explodes into a cloud of flying shards on the far side, and now you are being hit by dozens of fragments instead of one. Pile on more heavy shielding, and you are not building a wall. You are loading the wall. So the designers of the Ark have to think differently. Not heavier, lighter, and cleverer. The trick is to use materials rich in hydrogen, the lightest element of all. A cosmic ray striking a light hydrogen atom transfers its energy cleanly without blasting out that vicious shower of secondary particles. So instead of steel, the Ark leans on water, on hydrogen-rich plastics, and on the raw rock of that hollowed-out asteroid we spoke of long ago. Meters of stone and water wrapped around the living quarters, a womb of ordinary matter, patiently absorbing the bullets before they ever reach a human heart. And some dream of going further, of building an active shield, a powerful magnetic field around the ship, an artificial version of the one Earth uses to sweep charged particles aside before they ever arrive. In principle, it could work beautifully, but powering a magnetic shield strong enough to protect a whole world and keeping it running without fail for 4 centuries remains purely theoretical. We have never built anything close. So for now, the Ark's best defense is the oldest one imaginable: thick rock and deep water and distance, and radiation, it turns out, is only the patient killer. The sudden one is far more violent. Interstellar space is not perfectly empty. Scattered through it, impossibly thin but never entirely absent, drift tiny grains of dust, specks of rock and ice and soot, most of them far smaller than a grain of sand, floating in the black. At ordinary speeds, a fleck of dust is nothing. You breathe in thousands of them a day. But the Ark is not moving at ordinary speed, and here a single brutal piece of physics turns everything monstrous. The energy of an impact depends on the square of the speed. Double your speed, and the punch quadruples, and the Ark may be crossing the void at 1/10 of the speed of light, around 30,000 kilometres, nearly 19,000 miles, every single second. At that velocity, that harmless little speck of dust is no longer harmless. It carries the energy of a bomb. Let that land for a moment. A single grain, smaller than a mote you'd see floating in a sunbeam, striking the hull at 1/10 of light speed, releases a flash of energy like a small explosion, vaporizing itself and blasting a crater into whatever it hits. Physicists who have run these numbers describe an unshielded ship at these speeds being steadily eaten away, gnawed at by particles smaller than sand, each impact a pinpoint detonation. Now picture that, not once, but continuously, for centuries. A ceaseless, invisible sand blasting at a fraction of the speed of light, every grain a tiny bomb, hour after hour, year after year, for 400 years. How could anything survive that? The answer is as elegant as it is unsettling. The Ark cannot simply armour its hull because the impacts are too violent and too constant. The front of the ship would be ground away. So instead, the designers propose sending a shield out ahead of the ship, a broad, tough barrier flying far in front, perhaps kilometres forward, taking the hits so the ship never has to. Any grain of dust in the Ark's path slams into that forward shield first, and at these speeds, the collision doesn't just stop the grain, it vaporizes it, blasting it into a harmless spreading puff of gas long before it can reach the crew. The ship rides safely in the wake. Sheltered behind a wall, it pushes ahead of itself through the dark, like a swimmer held safe behind a breakwater as the waves shatter against the stone. The crew, sealed in their rock and water and darkness, might never even feel it, and they would need every ounce of that shelter, because the next blow that comes for them cannot be stopped by any shield ever devised. It arrives not as a particle, but as a message. Imagine it. Generations into the voyage, the Ark's instruments detect something ahead. A signal, coming from the very star they have spent centuries crawling toward. And the signal says, someone is already there. Because while the Ark has been inching across the dark for hundreds of years, the civilization it left behind did not stand still. Newer, faster ships, built with technology the founders could only dream of, launched long after the Ark departed, could have raced past it in the night and reached Alpha Centauri first. The crew that sacrificed everything, generation after generation, might arrive to find the destination already settled, the frontier already a colony, their entire epic 4-century voyage rendered pointless before they even arrive. And here is the chilling part. We saw this coming. Right at the very beginning, we met the weight calculation, the cold arithmetic warning that leaving too early might mean being overtaken by something faster. This is that warning, made real. The trap that shadowed the mission from the first day, closing at last. The idea is old, and it has haunted this dream for generations. Back in 1944, before we had ever left the atmosphere, before a single human had orbited the Earth, the writer A.E. Van Vogt published a story called Alpha Centauri. In it, a crew crosses the vast dark to Alpha Centauri, only to arrive and discover the system already colonized, settled long ago by people who left Earth centuries after they did, aboard ships fast enough to overtake them completely. 80 years ago, we already understood exactly how this heartbreak could unfold. So place yourself aboard the Ark in that moment. You are the final generation. Your entire family line, every ancestor you ever had, back to the founders themselves, spent their whole lives carrying this mission forward. And now, closing on the destination, you learn that others beat you to it, that the sacrifice of a dozen generations bought a colony someone else already built. What do you do with that? Do you turn your grief into rage, or do you find another meaning entirely? Because there is another way to see it. Perhaps the Ark arrives not as pioneers, but as long-lost family, met by descendants of Earth who have been waiting, who can offer help and knowledge and a welcome. Perhaps the voyage was never only about being first. Perhaps it was about the crossing itself, about the extraordinary fact that a fragile thread of human life held together across 400 years of nothing and made it. The crew must decide for themselves whether their voyage still holds meaning, and that is a decision no engine and no shield can make for them. But whatever they decide, one thing does not change. The star ahead keeps growing brighter, and then, after centuries of darkness, it happens. The pale red point that guided them for 400 years swells until it outshines every other star in the sky. It stops being a destination on a map and becomes a sun, close enough to feel, close enough to fear. The final generation now faces the single hardest maneuver of the entire mission, the one problem we flagged at the very start and set aside. They have to stop. Remember, reaching the star was never even half the battle. A ship traveling at a tenth of light speed that cannot brake will simply flash through the system in hours and vanish forever into the dark beyond. To actually arrive, to stay, the Ark must shed all that monstrous speed it spent centuries building up, and so it reaches for the elegant solution we uncovered long ago. The magnetic sail unfurls. Picture it opening in the dark, a vast invisible loop of magnetic force spreading out around the ship like a colossal parachute made of pure field. And as the Ark rushes through the thin charged gas drifting between the stars, that field grips the gas and drags and pulls back, bleeding away the speed a fraction at a time, not in a day, not in a year. Slowly, patiently, over decades, the great ship leans back against the interstellar wind and begins, at last, to slow. For the first time in 400 years, the destination is no longer a story the old people tell, no longer a myth or a promise or a pale red star on a screen. It is real. It is right there, filling the sky ahead. And the descendants of the founders, strangers to Earth, strangers to everything but the inside of their ship, are about to become the first human beings in history to arrive at another star. The question is what, exactly, is waiting for them when they do. For decades, the Ark bleeds away its speed. There is no dramatic braking, no shudder of engines, just the vast magnetic field dragging against the thin gas between the stars, hour after hour, year after year. The ship leaning back against the emptiness like a rower pulling against a current. An entire generation is born into that deceleration. Some will grow old and die during it, never knowing anything but a world that is slowly, imperceptibly coming to rest. And ahead of them, growing brighter with every passing year, burns the reason for all of it. Proxima Centauri, a small, dim red ember of a star, the closest sun to our own, and the destination that pulled a dozen generations across the void. From the ark's windows, it no longer looks like a star at all. It looks like a fire seen from across a dark field, deep red, restless, close enough now to throw light across the hull. They made it. After 400 years, human beings have crossed to another star. But the universe has one more twist waiting, because the destination itself may betray the very dream that launched the mission. Proxima b, the rocky world in the habitable zone, the prize that justified everything, is almost certainly not what the founders imagined. Here is the first problem. Proxima b orbits its star roughly 20 times closer than the Earth orbits the Sun. It has to. Proxima is such a faint, cool star, putting out well under 1% of our Sun's visible light, that the only place warm enough for liquid water sits right up against it. How close is that, really? Proxima b completes an entire orbit in about 11 days. Its whole year, spring, summer, autumn, winter, if such things existed there, passes in less time than a fortnight. You could take a 2-week holiday and return older than that planet's entire year. And when a world hugs its star that tightly, gravity does something strange over the ages. It slows the planet's spin gradually until the rotation locks to the orbit, and the same face is turned toward the star forever. Astronomers call this tidal locking, and we can see it happening in our own sky. The moon is tidally locked to Earth, which is why you have only ever seen one side of it in your entire life, the same familiar face, every single night, for all of human history. Now imagine that happening to a world with an atmosphere and possibly an ocean. Picture yourself standing on that surface. On one hemisphere, the star never sets, a swollen red sun nailed motionless to the sky, never rising, never dipping, casting shadows that never move. Behind you, if you walked far enough, you would cross into a hemisphere of permanent night, where that sun has never once risen and the cold never breaks. One face in endless dusk-red daylight, the other in endless dark, and between them a narrow ring of twilight circling the entire planet, the only band where the temperature might be survivable at all. That is not necessarily fatal to life. A thick enough atmosphere could circulate heat from the scorched day side to the frozen night side, smoothing the extremes into something survivable, the way ocean currents on Earth carry warmth from the tropics to the north and keep whole continents from freezing. Some astronomers think habitable conditions there remain genuinely possible, and if they are right, imagine what a colony on that twilight ring would actually be. A settlement built along a permanent sunset, in light that never changes, on a world where nobody would ever have a word for morning. Children born there would grow up never seeing a sunrise, not because the sky is closed as it was aboard the ship, but because their planet simply does not do that. But every bit of that hope depends on the atmosphere surviving, and that is where the real trouble begins, because Proxima Centauri is not a calm, steady sun like ours. It is what astronomers call a flare star, a small red dwarf with a violent temper, prone to sudden, enormous eruptions of radiation. We have watched it happen. In March of 2016, a telescope array recorded Proxima erupting in a superflare so powerful that the star briefly brightened by nearly a factor of 100, flaring for a few moments into something faintly visible to the naked eye from a dark sky. A star normally far too dim to see without a telescope, suddenly bright enough to notice. Now remember how close Proxima b sits to that fire. Researchers estimate that for a flare of the same energy, the planet receives radiation something like 400 times more intense than Earth would from our own sun. And these outbursts are not rare events. Studies suggest large flares hit that world several times a year, every year, for billions of years. The consequences are brutal. Modelling of an Earth-like atmosphere at Proxima b suggests that this relentless flaring could strip away 90% of the planet's protective ozone within just 5 years, and destroy it entirely over longer spans. Ozone is the thin molecular shield that absorbs ultraviolet light. Remove it, and the surface bathes in radiation strong enough to kill even the hardiest microorganisms we know of on Earth. And the deeper worry runs beyond ozone. Over billions of years, that ceaseless barrage of X-rays and stellar wind may have simply blown the planet's atmosphere away into space, leaving behind not a living world, but a bare, scoured rock in the habitable zone, warm enough for oceans it no longer has. We should be honest here, because scientists genuinely are. Nobody knows. Some researchers argue Proxima b could have retained a substantial atmosphere and might still hold habitable conditions in that twilight band. Others conclude the flares almost certainly stripped it bare long ago. The debate is real, unresolved, and it will likely take the next generation of telescopes to settle it. We simply do not yet know whether the nearest possibly habitable world is a garden or a corpse, and that other candidate, the faint giant world that the James Webb Space Telescope glimpsed beside Alpha Centauri A, then failed to see again, offers no comfort even if it turns out to be real. A planet of that size and mass would be a ball of gas, something in the family of Saturn. No surface to stand on, no ground to farm, nothing a colony could ever call home. So consider what may greet the descendants at the end of everything. They arrive after 4 centuries. 16 generations lived and died to bring them there, and what waits could be a tidally locked rock with no air, orbiting a star that erupts several times a year, and a gas giant they could never touch. No fields, no oceans, no open sky, no living ground at all after every possible sacrifice. And yet, even here, the story does not simply end in defeat, because Proxima is not alone. Remember that Alpha Centauri is 3 stars, not 1, and the other 2, A and B, are not dim red embers at all. Alpha Centauri A is remarkably sun-like, slightly more massive than our own star, and about half again as bright. B is a little smaller and cooler, but steady. 2 calm, ordinary suns of exactly the kind that warmed the Earth for 4 billion years. And here is the extraordinary part. Proxima currently sits roughly 0.2 light-years from that pair, about 13,000 times the distance from the Earth to the Sun, which sounds enormous until you compare it with what the Ark has already survived. That gap is about 1/20th of the crossing they just completed, a voyage that consumed 400 years and 16 generations, and the next hop to genuinely sun-like stars might take 20, a single lifetime. One captain could leave Proxima as a young woman and arrive with her hair gone grey. After everything, the hardest part was always the first step out the door. And here is where the story turns quiet and strange and unexpectedly beautiful, because if there is nowhere to land, they simply keep living. The Ark does not need a planet. It never did. It has spent 400 years being a world in its own right, growing its own food, breathing its own recycled air, spinning its own gravity, repairing itself without a single delivery from outside. It can settle into orbit around Proxima and continue exactly as it has, except now with something the founders never had: a sun, a nearby star to power the farms and lights forever, asteroids and raw material to mine, a place to build more ships and more worlds if they choose. They would become a civilization living beside a star they can never walk upon. And think about who these people are. They are strangers to Earth, a planet none of them has seen, that exists for them only in old recordings and older stories. And now they are strangers to this new sun as well, arriving at a place their bodies were never shaped for, that may offer them nothing but light. They belong to neither world. They inherited a mission chosen entirely by people who died 4 centuries before they were born and carried it to its end anyway. So did they succeed? Did any of it work? To answer that, we have to go all the way back to the question we started with. How could a generation ship truly reach Alpha Centauri? We have spent this whole journey chasing that question through engines and shielding and genetics and grief. And the answer, when it finally arrives, is not the one most people expect. Not by moving fast. Every attempt to solve this problem with speed, the bombs, the fusion drives, the antimatter we cannot make, runs into the same wall. Interstellar space is simply too vast to be beaten by velocity. A generation ship crosses instead by moving slowly and never once stopping, not a sprint, an unbroken, patient 400-year pull through the dark. Not by carrying people either. That is the deeper answer. No human body survives the crossing, and no shielding or medicine changes that. What the Ark actually carries is not passengers, but a lineage, a chain of lives, each one handing the mission to the next, all the way across. And so the ship succeeds only by ceasing to be a ship at all, by becoming a world, a recycled breath passed from lung to leaf and back again, a gravity made from nothing but spin, a closed sky handed down, generation to generation, like an heirloom nobody is allowed to break. It reaches the stars the way a river reaches the sea. Not by any single drop of water making the journey, no drop does. The water that leaves the mountain is never the water that meets the ocean, but by the whole flowing body of it, carried forward, always onward, each part handing its motion to the next. The ones who arrive never met the ones who chose to leave. They share no memory, no language exactly, perhaps not even quite the same genes. And yet they are not separate voyages. They are one single, unbroken crossing, carried through the dark by people who each held it for a while and then handed it on. Every calculation we have followed, the fuel, the farmland, the crew size, the shielding, the ethics, points quietly toward the same truth. Crossing to another star is less an act of engineering than an act of inheritance. Right at the beginning, we said that a generation ship asks people to plant a seed in soil they will never walk, for shade that will fall on someone they will never meet. Now we know what that really means. The founders were never the ones who planted the tree. They were the seed. Everything after them, the births, the funerals, the harvests, the repairs made by hands that never touched earth, was the tree growing, slowly, in the dark, and the descendants standing at the window, watching a red sun rise over their new home, are the shade at last, the thing the founders imagined but were never, ever going to see. That is the price of admission. Not money, not fuel, not even courage exactly. It asks an entire civilization to begin something it has already accepted it will not finish. More than a century ago, in a letter written in 1911, a nearly deaf Russian schoolteacher named Konstantin Tsiolkovsky, the same man whose merciless rocket equation still governs every engine we have ever built, wrote a single line that has followed us ever since. Earth, he said, is the cradle of humanity, but one cannot live in a cradle forever. A generation ship is simply what leaving the cradle would cost, and whether we ever build one, whether a single ark is ever hollowed from an asteroid and pushed into the dark, the dream itself reveals something exact about who we are. Because look at what we are actually doing. We are a species that looks out at 40 trillion kilometres of freezing, silent emptiness, 25 trillion miles of nothing between us and the nearest star, and instead of turning away, we run the numbers. We argue about crew sizes and ozone layers. We build sealed glass worlds in the Arizona desert and lock ourselves inside to see what breaks. We ask, seriously and soberly, whether our great-grandchildren's great-grandchildren might one day cross it. That impulse may be the strangest thing about us, not the technology, the willingness to care about something that will happen long after everyone alive today is gone and forgotten and dust. Tonight, when you next find yourself outside in the dark, look toward the south if you can. Somewhere in that sky sits a point of light that is 3 stars, not 1, the closest thing to a neighbor our sun has ever had. 4 light years away, close enough to dream about, far enough to cost a civilization everything it has. It is not coming any closer. The stars will never come to us. So one day, perhaps, slowly, patiently, across 400 years of darkness, carried by people who will never see the far shore, we go to them. Before you go, sit with one last thought. Everything we followed tonight, the sealed world, the sacrifice, the promise carried across 400 years by people who never saw the end of it, none of that is really science fiction, because it already happened. To you. Think back far enough along your own bloodline, and you will find someone who kept going through a winter they did not expect to survive, someone who stayed awake beside a sick child, someone who planted and built and endured and was afraid and kept going anyway. They never knew your name. They never knew you were coming. Most of them are not remembered by anyone alive today. No photograph, no grave anyone visits. Nothing left but the fact that you are here. And still, every one of them handed something forward. Life passed from hand to hand across thousands of years of darkness until it reached you. You were the arrival. You are the shade that fell on ground they never walked. That is why a generation ship is possible, not because of the engines, because we have already done it, slowly on foot, on this one small world, for longer than we can remember. Thank you for staying with me through all of it. Journeys like this one are only worth making because someone is on the other side of them, listening. If tonight meant something to you, a like and a subscribe is how I know you are here. More quiet journeys are coming. I hope you'll be there. Sleep well. Someone long ago made sure you could. Good night.